So, as poor as that is, that's the symbol for a resistor, right? Okay. So if I see that in a schematic, I immediately know that there's a device in my circuit. It's called a resistor. So let's talk about electrons in a resistor. What's really happening there?
Limiting the flow.
Okay. So if it had copper wire in it, let's say ideal, okay? There'll be ideal and then there'll be real. And when we do labs, we'll find out what real is. And we'll find out that real is different than ideal. It looks good on paper, but doesn't always work on the breadboard, okay? But that's good. Then we learn, okay? So in a resistor, we're going to probably guess that they don't just use copper wire, right? They have to use some kind of resistive material. So instead of using on those ends or in the metals, they got to find something that will flow electricity. It's not an insulator, but it won't flow it completely ideally, so it's not a conductor, right? Somewhere in between, right? So a resistor falls in between. What do they use in a resistor? You guys know?
Like carbon or
Car- Carbon, yes. Ceramic is the layer that actually holds the carbon. Most of them are carbon film. There are some that are wire wound. I don't know if you guys talked about wire wound or not. In a light bulb, there's a resistor, not in the new ones, the old ones that come from Mexico now. But they use a resistor in there to make light, and it actually turns out to make heat also. What do they use in a light bulb? Filament. What's it made of? Tungsten. Tungsten has a particular property, just like carbon, that allows us to resist the flow of electrons, right? What does that really mean?
Just gonna put one in on another, and the other side will be lower.
But we have the same amount of electrons go in as come out.
Stacks them up.
Stacks them up. What's really happening in there? Okay. So if I put an electron in, it runs down the copper wire and it hits the resistor. The resistor, the atoms in the resistor hang on to the electrons just a little bit harder than the copper does. But they don't hold on to them permanently. It's just a lot harder to get them to move across. Okay? And once they pop out the other side, then they're on the copper wire, they're gone. So always remember, the number of electrons that go in are the number that come out. They just have a harder time getting through. Okay? And when they have a harder time getting through, what do we generate? Heat. You say, well, you know, my resistors don't get warm. They do, but you don't know it because there's very little heat given off. If they give off a lot of heat, they burn up. So you can see where if we have a short and a resistor smokes, that means there was so many electrons going through there and it was trying to hold them back and it generated so much heat that it burned up. Okay? So we either had a problem with the circuit or we designed it with a resistor that's too small or whatever. Okay? So back to it. When you think about a resistor, you have to remember the electrons that go in are the same number that come out. They're just resisted in their flow because of the atoms holding on to those electrons a little harder. So how do we do that? Well, if we use carbon or tungsten, but carbon in resistors for film, what we do is we use more or less. More or less will make them hold on more or less. If we have more of them, we can get more through. Even though they're holding on, get more through, okay? So we change the amount of carbon in the film, and it changes the resistance to the flow of electrons through there. And we have a resistor. Now you guys knew that already, but you might not have known just how it did that. You always have to remember it generates heat. In fact, when you figure out the power rating, you really are figuring out in wattage the heat that can be given off. Because in physics, you know that when you figure out a wattage, that actually tells you the amount of thermal heat that actually the device is emitting or absorbing, right? Okay. So, and we're going to do power ratings too. Okay. So now let's just talk about this resistor. Most resistors start, well, you can have resistors that start at less than 1 ohm. I can have a 0.1 ohm. Everybody knows the little top hats ohms, right? You guys dealt with that, no problem. If I have a 0.1 ohm resistor, why would I even have a 0.1 ohm resistor? Isn't that really, 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 really tiny?
Could be a microcontroller or something that's.
How about a fuse?
Okay.
Fusible resistors usually are 0.1 ohm. And they just burn out and you put a new one in, you know. Because fuses are a mechanical device and they're expensive to build. A fusible resistor is really cheap. You just slap it in there. And usually just have one band on them, you know, or they're denoted 0.1, okay? So these usually are fusible resistors here. Not always, but for the most part, they are fusible resistors, okay? And then you go from, say, 1 ohm to 1 meg ohm. Meg stands for million. There is a chart in your book under resistors. It's chapter 1 basically is what we went over with the atoms and all of that. It does show a materials list for conductors and also for insulators. And it just does a little bit on voltage and resistance at the end of the chapter, and then we end up in chapter 2, which is current. So what we'll do is we'll work on that last page there, talk about the resistance, the voltage, and the current. We're getting pretty close here. We're just going to review. This is all review for you guys. I know it is. You guys all went through this. You all talked about it. Okay, so 1 is a million ohms. There is a chart in the book under, let's see, Ohm's Law. Quickly get to Ohm's Law here and see where that chart is. Shows a chart for, oops, don't see it.
The prefix is on page 16.
16, that's what I'm looking for. So go to page 16, thank you. The prefixes, tera, I have never seen a tera resistor. That's almost an insulator. Giga, I've never seen a giga resistor either. But mega, kilo, milli, micro, nano. Okay, so mega and kilo will be for resistances. You'll see that a lot. Milli, micro, nano, and pico, you'll see that in capacitors and inductors, okay? So these prefixes are nice to mark in your book because I can never remember how many zeros there are for the prefix. So when I'm doing a calculation, if I need to know that, I can just tab right over there and say, oh, there's 6 zeros or there's 10 zeros, whatever, you know, and you can make the movement in your calculations, okay? So it's nice to have that tagged in your book. I got those little sticky things that are colored. I just stick those in there. My books have all these things stuck all over them, you know. Once in a while I end up finding a check or something in them. It's kind of cool. No money though. All right, so we will probably see resistors in this range. 1 ohm, pretty close to a wire. Meg ohm, pretty close to an insulator. 1 ohm you'll probably see in high watt, because if there's any current, you got to have a pretty high wattage resistor to be able to stand the current if it's at 1 ohm. Mega ohm, usually pretty small resistors because there's not a lot of current through them, so you don't need to have a whole lot of power. Mega ohm resistors are used where there is not a current flow. There's a voltage difference in an amplifier or something like that, but not a lot of current flows. Okay, I don't see a lot of them, but you'll see.